The product rule also follows a certain pattern. Check out an example of differentiating a product. Welcome to differential calculus. Let's recall a pattern of the product rule. Having two functions, f of x and g of x, we differentiate their product by copying the first term and differentiating the second term. Then add to this term the second term copied, multiplied by the derivative of the first term. The practice example for this video is y given as the quantity of negative 10x squared minus 7 times the fifth root of x squared plus 9, multiplied by the binomial 2x cubed plus 4. Check that the second term of the first quantity has a radical sign, and it would be easier for us to work when the sign is eliminated. We do that by converting it into a fractional exponent instead, making the function y as the same terms with the converted radical term as negative 7 times x raised to 2/5. Now that we have everything differentiable, perform the product rule. dy over dx is then the first term copied multiplied by the derivative of the second term, 2x cubed plus 4, then add the second term times the derivative of the quantity negative 10x squared minus 7x raised to 2/5 plus 9. We cannot further simplify the copied terms for now, but we can distribute the derivative in each term of the second factors. By doing so, dy over dx becomes the copied term of negative 10x squared minus 7x raised to 2/5 plus 9 times the distributed derivative of 2x cubed plus the derivative of 4. Add to this the copied term of 2x cubed plus 4 multiplied by the distributed derivative of negative 10x squared minus the derivative of 7x raised to 2/5 plus the derivative of 9. At this point, we can then conclude the derivatives of 4 and 9 as 0 because they are purely constants. The derivative is somehow shortened by zeroing out some terms, giving the current dy over dx. We then use other differentiation rules, starting with the constant multiple rule. Set out in front all constants and treat them as coefficients. So the function of dy all over dx still has the copied first term times 2 times the derivative of x cubed plus the second term times the differentiable quantity of negative 10 times the derivative of x squared minus 7 times the derivative of x raised to 2/5. The next step is to differentiate using power rule. But what is power rule? It states that the derivative of x raised to the power of n with respect to x becomes the exponent n times the variable x raised to its original exponent n minus 1 times dx over dx. We are then ready to differentiate the terms. dy over dx then becomes the copied first term times the coefficient of 2 with a derivative using power rule. That is 3 times x raised to 3 minus 1 times dx upon dx. Add to this the copied second term times negative 10 with 2 times x raised to 2 less 1 with dx over dx minus 7 times the original exponent of 2/5 times x raised to 2/5 minus 1 with dx upon dx. Finally, we can dissolve dx as dx upon dx cancels out as 1. Simplify dy over dx as the copied first term times 6x squared plus the second term times negative 20x minus 14/5 of x raised to negative 3/5. This is the end of the differentiation, and the next steps to happen are just to simplify the answer using algebra. So take out parentheses by distributing terms. dy over dx then becomes negative 10x squared times 6x squared as negative 60x raised to 4. Next is negative 7x raised to 2/5 times 6x squared, giving negative 42x raised to 2/5 times x squared. The third term has 9 multiplied by 6x squared, giving 54x squared. For the next term, we employ the FOIL method. 2x cubed times negative 20x is negative 40x raised to 4. The next term has 2x cubed times 14/5 of x raised to negative 3/5. For now, take this as negative 28/5 of x cubed times x raised to negative 3/5. The third term has 4 times negative 20x, giving negative 80x. Then the last term has 4 times negative 14/5 of x raised to negative 3/5, simplified as negative 56/5 of x raised to negative 3/5. Next is to simplify x with fractional exponents. By working on equivalent fractions, we get negative 42x raised to 2/5 times x raised to 10/5, which makes it easier to add fractions, giving negative 42x raised to 12/5. The second term has negative 28 over 5 times x of exponent 15/5 times x raised to negative 3/5. And by adding exponents, the term becomes negative 28/5 of x raised to 12/5. The simplified derivative then becomes the following, where we can easily collect similar terms. Take negative 60 and 40 together, making negative 100x raised to 4, followed by negative 42 minus 28/5 with x raised to 12/5, and they are collected as negative 238 over 5 times x raised to 12/5. The rest of the terms are merely copied, plus 54x squared minus 80x minus 56/5 of x raised to negative 3/5. Note that aside from having fractional exponents, there is also a negative exponent of x. So, make it positive by taking its reciprocal, making the last term as negative 56 over 5x raised to 3/5. For the final step, revert back the answer into one with radicals to conform with the format of the premise. Transform all fractional exponents into radicals, keeping the other terms just as they are. But the second term becomes negative 238 over 5 times the fifth root of x raised to 12. And the last term also becomes negative 56 divided by 5 with the fifth root of x cubed. An alternate solution to solving derivatives of products is to simplify the function as early as possible into simple terms. So instead of using the product rule, we take out grouping first by multiplying terms. Negative 10x squared times 2x cubed is negative 20x raised to 5. Negative 7 times the fifth root of x squared multiplied by 2x cubed is negative 14x cubed times the fifth root of x squared. The other term is multiplying 9 with 2x cubed, giving 18x cubed. The next three terms has a factor of 4. That is, 4 times negative 10x squared, which is negative 40x squared. There is also 4 times negative 7 with the fifth root of x squared, and that is negative 28 times the fifth root of x squared. The last term has 4 times 9, giving 36. Let's then convert the radicals. The second term becomes negative 14x cubed times x raised to 2/5, where, by equivalent fractions, the term becomes negative 14x raised to 15/5 times x raised to 2/5. Add the fractional exponents and have negative 14 times x raised to 17/5. The next term becomes negative 28 with x raised to 2/5. Place these two terms into the function and have y as equal to negative 20x raised to 5 minus 14 of x raised to 17/5 plus 18x cubed minus 40x squared minus 28 raised to 2/5 plus 36. Taking out the parentheses, we are then ready to differentiate. Note that the last term applies the constant rule, making the whole term a 0. Start by setting out the constants. So dy over dx becomes negative 20 times the derivative of x raised to 5, which is 5x raised to 4 times dx over dx. The second term has a coefficient of negative 14 times the derivative of x raised to 17/5, which is 17/5 times x raised to 12/5 times dx upon dx. The third term has a coefficient of 18, then the derivative of x cubed as 3 times x squared with dx over dx. The following term has negative 40 as coefficient, then the derivative of x squared is 2x times dx over dx. The next term is negative 28 with the derivative of x raised to 2/5, which is 2/5 of x raised to negative 3/5 times dx upon dx. All dx over dx then cancel out to 1, and the derivative becomes negative 100x raised to 4 minus 238 over 5 of x raised to 12/5 plus 54x squared minus 80x less 56x raised to negative 3/5. This is practically the answer. But if we wish to adopt the format of the premise, transform the exponents into radicals, making dy over dx as negative 100x raised to 4 minus 238 upon 5 of the fifth root of x raised to 12 plus 54x squared minus 80x less 56 upon 5 with the fifth root of x cubed.